Okay, here's the next problem. We have gallium nitride, a band gap of 3.4 eV. This has to do with electrons absorbing and emitting energy. So if we elevate the electron energy, so this is positive energy, and we bring an electron up, we go from a low energy state to a high energy state, and the energy gained equals 3.4 electron volts, which is 3.4 times the charge on the electron. A charge times a voltage gives you an energy. Well, the electronic charge is right there. Remember, usually electronic charge is expressed as a positive number. We remember that protons have a positive this amount of charge. Electrons have a negative this amount of charge. Okay. For beginning students, getting this straight is a bit problematic. Okay, so the energy the electron gains going up to the higher energy state will be this much. We'll calculate it in a second. When it drops back down from the high state to the low state, it's going to lose this much energy and give off a photon. And that photon will be the same amount of energy. The electron loses, the photon gains. Okay, let's go calculate it. So 3.4 times the electronic charge, and that's an equal sign, and a coulombs times a volt will give us 5.45, rounded to 3 sig figs. 5.45 times 10 to the negative 19th joules of energy. A coulomb volt is a joule. Okay, so how much energy does the electron lose? It loses this much. What is the photon energy? Photon energy is also this much. Whatever the electron loses, the photon gains. So this answers A and B. Wavelength of the photon. We just simply use energy of the photon is Planck's constant. Where is that in my constant list? There we go. Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength. And we are looking for wavelengths, so the second part of this is what we would use. Do I have the speed of light written down here somewhere? I do not. Okay. So, and that's probably something, yeah. Okay. Solving this, wavelength is going to equal hc over energy. And this is now a plug and chug problem. Well, there's the energy. I just take the reciprocal of it and multiply it by 6.63 e to the negative 34th times speed of light 3 e to the positive 8 equals 3.65 times 10 to the negative 7th. 365 nanometers. It's bluer than blue. It's kind of into the ultraviolet range, real close to the top end of the visible light spectrum. Okay, so that is part A. Part B, or excuse me, that's part C. What is the photon wavelength? There we go. Now, what would be the wavelength of an electron? If an electron had this much energy, ignoring relativistic effects, what would be its wavelength? So the kinetic energy of an electron is 1/2 mv squared, or momentum squared over 2m. The wavelength of that electron is h over the momentum. Well, solving this momentum equation, P equals the square root of twice the mass times the energy. So we're going to do this problem twice, actually. First, wavelength of an electron. Second, wavelength of a proton. And we have the mass of a proton up here. Here's the mass of a proton. Here's the mass of an electron. So we can rewrite the equation. H over square root of 2me. Now it's just plug and chug. We use mass of the electron here, and when we get mass of the proton, the formula is going to be the same. The wavelength of a proton, excuse me, the formula is going to be the same, except we're going to use the mass of the proton. And of course, a hydrogen 1 nucleus is a proton, so that's why I'm writing this as a hydrogen 1 nucleus. Up here, we used MP for mass of proton. The rest of this problem is plugging and chugging. This answers part D, wavelength of the electron, and this answers part E, wavelength of the proton. Clear. 6.63 times 10 to the negative 34th divided by, and I better give my parentheses 2 times mass of the electron, 9.11 times 10 to the negative 31st power times energy. Energy 5.45 times 10 to the negative 19th power. And close it up, take the square root. There we go, square root of the denominator, and hit the equal sign. 6.65 times 10 to the negative 10th. Very small. The wavelength of an electron is much smaller. You can resolve much smaller features. That's why the electron microscope has been so useful in science. Now, same problem. Now, the mass is going up. The wavelength is going down. Mass is going up. Wavelength goes down. So let's do this again. 6.63 exponential negative 34th power divided by, create the parentheses, 2 times mass of the proton is 1.673 times 10 to the negative 27th power times 5.45. That's the energy, is 5.45 times 10 to the negative 19th power. Close it up, take the square root, and hit the equals. I'm just kind of looking over things, just double checking my stuff. Hit the equal sign. 1.55 times, go back here, 10 to the negative 11th. Smaller yet. Okay, wavelength of a particle. Particles are waves, waves are particles. When we get to quantum mechanics, that's what we're talking about. This is a quantum mechanics type of problem. And that's all, folks. I will see you on the next video.